So here it is. The Hillstrom diagram summarizes the most important features related to suspended sediment. On the x-axis, it's the size of particles. You have different types of sediment, and you can sort them according to their size. Okay, and it's sort of a concept here. In fact, in nature, you always have a mixture of different sediment types. Here, you just assume you have sediments of essentially all the same size. Not a mixture of different sediment. You just either have clay with very small particles, less than 0 a hundredth of a millimeter, okay, or you have sand. Okay, sand is 0.1 of a millimeter to 1 millimeter, okay, or pebbles. Indeed, pebbles you can throw into the water. We have sizes of 1 centimeter plus. Yeah? So this is what's done here. You sort according to the dominant sediment size, and then this diagram tells you what threshold velocity do you need in order to erode sediment from the seafloor. It's this black curve. Okay, I switch on the laser, and it's this black curve tells you what current speed do you need in order to erode sediment. And you can see it's not a linear form. Okay, you need quite high speeds in order to erode clay or silt from the seafloor, because these materials are often sticky and have a very high compactive force, and you need speeds of 1 to 2 meters per second to erode them. Similarly, you need very high speeds to erode pebbles, or can hardly call it erode, but to essentially move them around. Okay, lift them up a little bit and check them around. Okay, so now the interesting bit of this curve is that there is a region where you need the only relatively weak currents are needed to move sediment or to erode sediment from the seafloor. You need something like 20 centimeters per second or more to lift up or erode medium-sized sand. Okay, this is the type of sediment that's most easily eroded from the seafloor, unless you have a organic biologic substances that provide stability to the seafloor. Okay, and this is already a very, very important feature. Okay, because some types of sediment can hardly be eroded from the seafloor. Others are very dynamic. And it's the suspended sand. This is often the key sediment that's subject to this, what we call littoral drift, the movement of sediment along shores. Okay, so the second feature here is what minimum mean velocity do you need in order to have deposition? Okay, so that the sediments fall back onto the seafloor. Let's just look at the medium-sized sand again here. Once the current speed falls below something like 5 centimeters per second here in this limit, sediment, the sand becomes deposited on the seafloor again. So you can imagine, if you have tides, that during each stronger tidal current, sediment becomes suspended and then be moved around until the velocity drops. You know, at high tide, low tide, the velocity might fall below the threshold, and then the sediment falls back, and so on. Okay, so now a highlight here is that this minimum value goes to very, very small threshold values for very fine sediment. What it means is that the very fine sediment, clay and silt, actually can stay in the water column essentially forever. Once it's in there, it can be moved around, can be dispersed, okay, and this can decrease the concentration, but it will never fall back to the seafloor because there's always enough turbulence to prevent this from happening. Okay, so highlighting the zone between erosion and deposition in this diagram is called, this is when the sediment, suspended sediment, can be moved around horizontally by currents. Okay, and you note that for very large particles, once the current speed drops a little bit, the pebbles actually don't move anymore. Okay? So essentially, you need a very high speed to move them a little bit. Once it drops a little bit, there's no impact or so whatsoever. So this is really important to understand the behavior of suspended sediment. Okay, so print this out, produce a big version of it like a wallpaper, put it onto your wall and study this, okay? And think about it. Imagine what happens.